Without further ado, let me introduce our first speaker. Dr. Tom Starke is the CEO of AAA Quant. He has a Ph.D. in physics and works as an algorithmic trader at a proprietary trading company in Sydney. He has a keen interest in mathematical modeling and machine learning in the financial markets. He has previously lectured computer simulation at Oxford University and leads strategic research projects for Rolls-Royce. Tom is very active in the quantitative trading community, running workshops for Quantopian, teaching people quantitative analysis techniques, and organizing algorithmic trading meetup groups such as Cyber Traders Sydney. So without further ado, Dr. Tom Starke.
Hello, can you hear me? So today I want to talk about reinforcement learning, and I guess most of you, when you're somewhere in algorithmic trading, you probably heard about reinforcement learning because it's sort of like it has the promise to be the holy grail of trading, because you have these machines that have solved really difficult problems like beating the world champions in games like AlphaGo, which is supposed to be the most difficult game in the world. And so you think, well, if this is working, why don't I apply this to financial time series? And so in the last year or so, I just looked into this a bit in order to see what is there, and just try to figure out what can you do to make this work for financial time series. And so there's quite a few lessons that I learned along the way, and I have to say in advance, I can't give you the Holy Grail, unfortunately, but there's quite a few things that we can learn from these machines. And today I just want to talk you through it a little bit and to show you what has been done, and also give you a practical code example. So it's going to be a bit of code. I found actually last year when I gave a talk here, I used code as well and showed people how it was done. Unfortunately today, because of the setup, I can't run it, but I'll just talk you through a little bit. And for me, at the beginning, it was looking at reinforcement learning. It was a bit overwhelming because it was just such a step up from normal machine learning. And then when I sat down, wrote some code, and just tried to get my head around it, I slowly got better. And then when I looked at it at the end, I thought, well, actually, it doesn't look too bad. So right now, we haven't got really good toolboxes yet for this, unfortunately. But actually, when you start these things more or less from scratch, it makes you also think about what you're actually doing, which is sometimes really helpful, rather than just applying this out of the box. So I just, actually, I'm aware that after my session, Tucker Balch will also talk about reinforcement learning, and he's a university lecturer, and he's probably much better qualified to give you the theoretical background. So I'll just really quickly talk you through a few things, but I don't want to go too deep into the theory, and rather come more to the practical aspects of it, because I find also in my work with leading quant teams that a lot of the people initially, they're very hungry for theory, but at the end of the day, once you've done the theory a little bit, you want to actually produce real P&L, you want to produce cash. And so yeah, theoretical stuff is great, but the practice is more important. So what is reinforcement learning? Basically, it's a machine that looks at a state of a system and then uses what we call a policy to take an action. And this has been initially really well applied to in games. So people have basically used them to beat computer games like Pac-Man and so on, and quite successfully. So in this case, we basically have a Markov decision process. So we go from state A, for example, to state B, and while we are transitioning that state, we get a reward, or we earn some reward or some points, so to speak. And what is important here is that sometimes when we go from a beginning state, let's say A, to state F, just choosing the path initially that gives us the highest reward doesn't eventually necessarily lead to the biggest reward going to the last state. And so normally it's quite difficult to figure out a way to get through this and actually find the optimal path that gives you the best payoff. And so reinforcement learning can help us with this. So when you start with this, basically there's these few key words that you really have to think about, which is the action, the transition state, the reward, and the policy. So it's really simple in a way. The action is whether you take, what path you take here, for example. The transition state is the next state that the system is in. Could be when we go from A to B, could be B, C, or E. The reward is basically what we get when we transition to either one of these states. And the policy is basically the set of action that we take to choose, or that we choose to get from here to there. And basically, the rewards we achieve at the end is basically what we define as value. And in trading, it could be fairly simple. It could be just our P&L, or it could be our Sharpe ratio if we want to get a bit better. Any of those. So I have those few slides choosing a policy. So there's, I just very quickly go through this. So there's different ways to pick a policy, and for example, you could just say, well, every time I go here, I just choose the path that gives me the biggest payoff. And as I said, it doesn't necessarily lead to the optimal path that gives you the biggest payoff at the end. So there is this idea in reinforcement learning of exploration versus exploitation, which means when we, for example, go to this path where we have those different choices, 2015 minus 2030, we could just exploit this and go with the biggest payoff, which is 30 here. Or we could say, well, actually, maybe if we don't choose the biggest payoff, if we choose another one, we might actually get more out of it at the end. And so this is what we call exploration. We actually choose, for example, just a random path and see what it gives us and see whether we actually move on to this with a higher payoff at the end. Okay, so I'll skip this slide just for time. And so when I started this, I thought, well, how can I really think about this whole problem set? Because there's really a lot of ways to think about it when you apply it to trading. And the obvious choice for me, at least, seemed that when you start with this, you look at what people have done, and they play games. So they basically have a game, they apply the machine to it, and then the game plays, and at the end you get a certain score. And over time, that score will improve. So in reinforcement learning, we could essentially do a similar thing. We could take an individual trade, for example. We have a time series. And by the way, I started with really simple stuff just to keep it like manageable. So we start with a simple time series, and rather than going through the whole time series or whatever, we actually start playing games. So we go through, the machine starts like learning, understanding something, and it gives us some idea of entry and exit. So in the simplest case, basically, the machine starts and it says, okay, enter here. And then it goes through the time series. You use your reinforcement learning process, which I'm going to show you later in code. And then at some point, it tells you to exit. And okay, this is pretty simple. And then when you have a really long time series, like 10 years or 15 years, it just keeps doing that. It just goes entry, exit, and every time it learns something based on the reinforcement learning machine. So over time, you can actually see that just in the case of computer games, the machine will actually start to pick up certain things in the time series and actually start to produce its own trading strategies bit by bit. And it's quite fascinating to see when you look at the machine. And in a sense, as traders, we usually come up with strategies. I mean, even though we've got all this new fancy stuff these days, my experience with working a lot of trading companies is simply that the good old simple trading strategies still do work quite well with slight modifications. So having this and having a machine actually telling you what trading strategy to use without you actually specifying anything is quite fascinating. So the question is, how do you train the system? There's several ways. You could basically say, well, I did running through each game individually and just moving along the time series. Another one would be to use the whole time series as one and then just run it over and over again. What I found, though, was I used several types of equities to train the system on. For example, if we use Apple, and you know Apple is mostly a increasing time series. It just basically makes money most of the time. The system just ends up in a long-only state, and that's really not what we want. So the next thing that we also need to consider is reward function engineering. So it's really easy. Like the reward could just be your P&L or your Sharpe ratio, but in reality, it's a bit more complicated. In fact, it's a lot more complicated than this, because if you say, well, it's my P&L, for example, if this system just gets into a long-only state, and it just basically gets into buy and hold, what does it, what does it mean? It just buys and holds at the end of the day. And this is perhaps not the strategy that you're interested in, and maybe it's also not the best strategy to choose at the end. It's just the one that the system picks. So perhaps in your reward function, you need to do something like punishing the neural network for actually staying in a trade for too long, and so on. So there's quite a lot of ways to train a reward function. You could also, instead of rewarding it with a P&L, you reward it with the P&L per tick. So just divide your P&L by the time it stayed in the trade. Another one is what features do we use for the neural network? This is quite important. In my case, I started simply with just a time series and a few modifications, and if we are traders, and in a sort of old school way, I applied some technical analysis indicators at first to see whether that does anything interesting. But of course, there's a lot more sophisticated ways to do this. How do we test the system? It's really understanding how the system actually performs overall, and it's actually not that easy with a reinforcement learner to really make sure that it runs the way it's supposed to run. And finally, what type of artificial neural networks can we use? We could just use a simple, your neural net, or we could use something like a LSTM, for example. I have tried quite a few, and I show you later. Actually, in my case, I found that simple neural nets are just as good as anything. So just a short word to the idea of the gamification of it. So turning trading into a game. And in a sense, and I have a lot of philosophical discussions about it, trading is a bit like playing a game. It's you start the game, something happens, and then you exit the game and you get a reward or a score. And so, in a sense, teaching a reinforcement learner or using it in that same sense is really an interesting one. And this is the first computer game I've ever played in the early 80s called Pong. I really liked it because it's pretty much the only game I ever stuck with in the end. And so in a way, trading is really not that much more complicated. you have a time series, a price series that just bounces around, and it bounces until it at some point exits the game, and then there's going to be some winner, or you're going to end up winning or losing, really. So in a sense, we look at the historical and current prices, technical data as inputs, and we have really just 3 actions that we can take. It's entry, exit, or buy or sell, or do nothing, and we end up with a P&L. So how do we train the system? And so I said before, we look at each trade as an individual game. We run through the price series in different ways. So initially what I did is I actually ran it randomly. So instead of running through the time series sequentially, what I did is just because I thought it was quite interesting, I jumped around. I just jumped to random places in the time series and played a game, and then I jumped somewhere else and jumped somewhere else, and just did this. The reason for this is it makes it not really path dependent, at least for the in-sample training. And so if you start, you enter a trade, and then at some point you exit, you enter, you always end up with this path dependency, because wherever you enter the first time then has repercussions all the way along the games that you play, because you got entries, or your next entry is really determined by where you exited, because you can't really enter again before you exited the last game. So jumping around randomly gets rid of this problem. So another way to do is the making the whole price series one single game. I looked at this as well, and as I said, that has certain limitations, because, for example, if you apply this to Apple equity, then you end up with a strategy which just turns into buy and hold over time. There's no more trading going on as such. And so what you could do is, when you use different instruments in this, you could train each instrument separately, which is a possibility. Or what you could do is you could play games, but you jump between instruments back and forth. Obviously, this is a difficult one, because even if you have different equities, they behave in a quite different way. And the question is, does it actually make sense to do this when you train a neural network? Because you might have some mean reverting or some trending time series, and all of these have different behaviors, and will our machine actually pick this up ad hoc as it enters the game? It's a difficult one to answer. So how do we design a reward function? In fact, designing reward functions, I found, is one of the real difficulties in this, and to do this properly. So we could, for example, use pure P&L on exit, but we could also have reward functions that reward the machine every time it makes a little bit of P&L, and punishes it if you lose a bit of money at every tick. So there is also, as I said earlier, punishment for long holding times. So, for example, if your hold time overruns by a certain time, your reward might go to 0 or go down to 50%, or some more complicated functions. There's also alternatives to using P&L as a metric. For example, you could do something like, if the machine recognizes the right trading direction, simply, not just the P&L, but it knows approximately when it needs to go, that would be a good alternative. Or even the recognition of which trading regime we are in. Does it end up looking or choosing some mean reverting process, or does it end up choosing some trending process? And that really comes then to something I talk later that actually picks up more the geometrical underpinning of the time series rather than just a pure movement of random ticks or random walks. So what features should we use? So initially, I looked at the most obvious technical things to use because I find it's always the easiest to use price action as a starting point. So in my case, I just looked at the candlesticks, open, high, low, close, and volume. Then I also applied a few technical indicators. I'm running it on Python, so I usually use a TALib, which is technical analysis library. It has a lot of these. One of the interesting ones, and this is, I think, quite a game changer, is to use time of day, day of week, time of year. Oftentimes, when we use this, we forget in time series to pick up seasonality, intraday seasonality, intra-week seasonality, and so on. So if you put this in as well, often that will improve things quite a bit. So the machine actually knows where it is at in terms of time, rather than just in terms of the price movement. Then, obviously, different time granularity is quite important. In the example here, I used 5-minute time bars, but you may as well use 1-second time bars, 1-year time bars, and it's up to you. The problem is that when you use larger time bars, the sample sizes or the number of samples that you have, basically the price data that you have, becomes less and less, and there's less chance for the machine to learn. So using a finer granularity is probably preferable because it is well known that reinforcement learners are quite sample inefficient. You need a lot of samples to get it to work. Then looking at other instruments as signals, obviously, and finally alternative data. So there's quite a lot of them, sentiment and so on. I haven't actually looked at alternative data, mostly out of time constraints. So, but I think this is actually where the real power of this lies eventually. How do you test the system? Initially, I thought, well, I just want to see whether it does anything. And so I started with just like really simple stuff, like sine waves and trend curves, and then I just used just a simple random walk. And then different types of artificial autocorrelated series. And then once I've done this, I've actually added some noise to the clean curves, like added some noise to the sine waves, added some noise to the trend curves. And then eventually I just used some reoccurring patterns. So I used some time series or some price series where I thought, well, they are quite mean reverting and so on. So I could actually have time series that really are understandable, and you can actually see, well, does the machine do anything? Can I test it? I think if you jump straight into a financial time series, which is effectively a random walk most of the time, then it's very difficult to tell whether the machine actually really does what it's meant to do. And starting with something simple and then ramping it up, making it more and more complicated is definitely, in my opinion, a much better way to go. So, I looked at different types of deep learning algorithms, just standard neural networks, and then I looked at convolutional neural networks. I did some work recently in image recognition for a different job. So convolutional seemed interesting. Also looked at SVMs or decision trees. You don't necessarily have to use deep learning as an output. You can actually go with something a bit simpler than SVM or simpler SVM and decision trees. In my work, actually, I found whenever I used machine learning in trading, support vector machines seem to work quite well a lot of the time. And I've seen some papers on it. I can't exactly tell you why that is. I tried to find out probably for the last 2 or 3 years why support vector machines seem to work for my purposes so well. If anyone has an answer, I'd be really interested to hear about it. Myself, I haven't really figured it out yet, but they seem to work well. And then finally, long short-term memory neural nets. They're somewhat new, and they're supposed to be really good for time series. They're usually used in speech processing and similar things like that. And natural language processing, where you have a pattern in time that persists. So it's kind of a natural choice to at least look at it. So next I want to show you a quick demo of what is a simple version of this looks like. And if you want, it's actually on GitHub. It's actually under this repository up there. If you're interested, I'll put it there. I warn you, it's not perfectly clean code. I'm a busy guy as well. Got a company to run. Work with a lot of trading businesses. So sometimes I have to make some concessions on my interests in other things. Okay, so first of all, there's quite a lot of obvious things. We parse data in from the time series. But by the way, the time series, or one time series to test on, is also included in the repository. So you see what the format is. It makes it a bit easier for you. And then I actually just use the same timestamps to create a synthetic series or some synthetic series. And you can see here I just got a sine wave, a bit of a trending series. Also add a bit of noise to them. So I've done, there's a lot more you can do, but for the purpose of this, I wanted to keep it relatively simple and really keep it as an example. So in reinforcement learning, probably the biggest thing that was developed a few years ago and the game changer to make this work was this idea of experience replay. And so without going too deep into this, it basically says that the neural network during the game, we gain a lot of experience from our previous understanding, and then we apply this experience and we use this thing called the Bellman equation or the Bellman model, and which then translates into something called Q-learning to the system in order to predict what action to take and on what's the optimal action to do. Initially, this was done purely using just patterns and Markov chain models, but using a neural network for this prediction has actually proven to be quite effective. And you can see here, this is really what is mostly associated with the reinforcement learning, and it's actually not a lot of code. And the Q-learning bit is actually only this little loop that we see here. So I don't want to go too deep into this. If you're interested, you probably just have a look at this yourself and go through. It's fairly straightforward to understand. And when you use it, you will see how it works. But what's important here is that it's actually quite a simple way to set up. So the next thing we need to do is we need to define what is the actual game in this. And so there's a few things that determine what our game constitutes, and one is state. So state is an interesting one. When I initially looked at how people did this reinforcement learning for games, you just see that people look at an image, and the image is, let's say, in the state in the case of Pong, it's just where our two bars are on the side, and then where's our little ball or our little pixel that moves around on the screen. And then you can quite easily translate this into a state for a time series. So rather than using the state as an image in the game, my image, so to speak, is just the time series that I want to look at. And so obviously I can't use the whole time series all the way to the beginning of time. I just need to take a snapshot, and usually what you do is you just start with the beginning of the game and you look back and you go, oh, okay, this is my time series. Now, the other thing is, though, as you go along, you actually gain more and more experience, and so rather than just using the look back from your one game, eventually a lot of the other understanding of the previous games will flow into the experience as well, and then help the neural network to make better decisions. So here we have those few things. We update the state, and then there's this thing called assemble state. It's basically one of the parts of our state is our time series, and in our case, I use open, high, low, close bars. But we can also add things to that. In this case, I add a few technical indicators and a few permutations of technical indicators. There's just a moving average, RSI, and momentum. I'm generally not, by the way, a big believer in technical indicators, but it seemed like an ideal choice to start with, so I thought it was quite interesting. Obviously, those technical indicators, as we probably all know, that they're not necessarily very predictive. In fact, some of them are quite lagging. But it might still be interesting for the neural network in terms of how it determines the state of the system, even though it might be lagging. So I thought it was quite good. Now, in this particular function here, rather than just using technical indicators, it's quite easy to see that you could just import alternative data, for example, or other time series prices. So let's say you want to look at some currency pair, and then you say, well, maybe this is determined by the price of oil, and then you could basically have price of oil in there as well as a signal asset, so to speak. There's a few convenience functions like get the last and time bars and so on. This is what I've been talking about all along. It's the reward, get reward. It's actually where you build your reward function. And that, as I said, is one of the real difficult things. And when you look at the literature, people talk about this designing reward functions. So that's the main thing. You then see there's quite a lot more there. I just want to go back to my talk and show you some results. If you apply a sine wave with no noise, and then halfway along about here, you switch it to a trend curve, what you can actually see is that the reinforcement learner picks that up extremely well. So as soon as you start a reinforcement learner, it just learns the sine wave, and then even if you switch it, it's about here, if you switch it to a trending curve, it then initially goes, oops, has a little bit of a wiggle, and then actually just keeps making money. Unfortunately, this is really not what we usually find. So the next step was, okay, we get a sine wave, but let's apply a lot of noise to it. And you can already see as soon as we apply noise, we have a lot less perfect P&L curves here, which is what you would expect. The same, this is a trend with a lot of noise. Again, it actually does perform all right, but it's still actually a very, very straightforward, simple time series overall. So some of you might recognize this price curve. It's just one that I picked for testing, and I actually used a lot of different ones as well. But this worked quite well. And if we just apply a really simple reinforcement learner with nothing else to this, we can see that it actually doesn't consistently make money. It really really sometimes you can see it falls into these local minima or optima, and then it does something, and it seems to like do well for a period of time, and then it just stops doing very well again. So one of the issues really that I found with those reinforcement learners is it really falls into these local optima, and we can really see that reinforcement learning is quite sample inefficient. When you actually use more and more samples, the machine will definitely improve its performance. Reward function design is hard, as I said before. The problem is that if you only reward the reinforcement learner at the end of the trade, your rewards are really sparse, which is also a problem. If you just always do give it a P&L at the end of the trading period, at the end of your trading game, the sparse rewards really can be difficult because of the calculations that need to be done to sort out. We do fall into a lot of local optima, and you see this when you run the reinforcement learner over and over again. And also as a result, we see that our results curves are quite unstable. They're very difficult to reproduce. So because of the nature of how reinforcement learning works on this, we have a real hard time to reproduce the results. And it's basically hard to do because financial time series are very noisy. It's really the noise that makes it. Like LSTMs and all these other fancy machine learning tools, they are really not designed to deal with a lot of noise. Image recognition doesn't have a lot of noise. Usually we have quite clear images. We can see the features. We can't often see the features in financial time series. Also, the rules keep changing. And also the rules evolve over time. And the other thing that is really a problem is computing power is still limited. We haven't really worked out a way to improve our computing power. Now, very quickly, I want to show you another result. So what I did here was, instead of using the time series as is, I just used a 5-period simple moving average for our price curve. And what we can see is suddenly, if we just have a curve a bit smooth, our reinforcement learner will actually really pick this up and produce some quite good P&L results. And what that shows is you can really, when you start using those machines, you should think about perhaps instead of just looking at pure noisy price series, maybe change your price series, give it some sort of geometric meaning, and then let the reinforcement learner rather look at this geometric meaning and then put something on top of it. It's easy to see. You can have the reinforcement learner basically go through a smooth price series and then have something on top that determines where you're at, and then maybe make trading decisions based on the other things. So there was a few more things to look at. And so here is an out-of-sample test. You can always look that up later. So I just want to say thank you. And the question is, are we there yet? I would say we're not quite there yet, but we're definitely getting closer. I think we're never going to find the Holy Grail, but let's keep trading. This is what makes it fun, and have fun exploring. And if you have any more questions, I guess my time is up. So, we've got 5 minutes for questions. Okay, so if you have any questions, please fire them away. Well, yes, we do, but what we assume when we jump around is that the structure in the time series is a lot less than the periods of time that we actually trade. So we have to live with that. Yeah, we can't just, we have to basically think those features that we would capture, we cannot capture as we jump around. So that's not something we can. Quite frankly, I've had some success with things with supervised learning in trading, and using usually SVMs, my favorites. But reinforcement learning, the idea of it is really, and this is what I said, it's kind of the holy grail. You don't actually have to give it a strategy at all. It can just learn as it goes along. So you basically let it run, and at first it does random things, and over time it will figure out its own trading strategy. And so for a trader or for someone who does algo trading, and you all know how hard it is to actually come up with good trading strategies, to have a machine that comes up with its own trading strategy, that's like amazing. We go like, oh wow, yes, I want this machine, you know. I don't even have to do the research anymore. The machine does it all for me. So that's the advantage of it. But yeah, as I said, the noise really makes it difficult. Now, the graph that I showed you using just a slightly smooth time series that suddenly gives us really interesting returns, I think that really tells us something about the potential that there is. But I would say it's not quite there yet to really do it. And the other problem is, if someone figures it out how to do this with proper time series and really get good consistent results, and then everyone does it, then the advantage goes away again anyway. So this is just the evolution of the market. So I think it would be a long way to go after all. This is actually what I mentioned before. When you or let's say a lot of people would apply reinforcement learning, then ultimately it will definitely affect the market. And what it would do is, as we probably all know, it would just make the market more and more efficient again, or maybe it just creates new inefficiencies that we haven't quite thought of yet. But ultimately, if reinforcement learning would be used heavily and would actually work, it would definitely affect the market quite significantly. And I would think probably more than anything we've seen so far, because it's such a big thing, like machines that learn by themselves. Because anyone could go and just switch a machine on like this. So you don't need skill anymore. You actually just need to press the power button effectively. So if I were to produce this machine and distribute it to everyone, then this is what would happen. So definitely there would be a large effect on the market. And that would maybe render these machines useless again, quite possibly. So thanks very much for coming. Thanks for listening.